Good morning. Most of the students have joined, so we shall start with today's aspect from the topic chemistry of block elements, wherein we have first of all we have finished the lanthanide elements, after which we have finished some methods of synthesis of transuranic elements, wherein we have studied that the first four members, that is actinium, thorium, uranium, and protactinium, these are the first four members which do occur naturally. Remaining all other members, they are synthesized artificially because they possess comparatively higher atomic masses, and hence these are also known as the SHE elements of the periodic table, that is super heavy elements of the periodic table, because they are having comparatively higher atomic masses. For example, last time we have seen that for Californium atom number 98, the atomic masses are about 250. So most of these elements which are situated after uranium, that is from atom number 93, neptunium to lawrencium atom number 103, all these elements are artificially synthesized or man-made elements. So we have also concluded that these elements are also known as the TU elements, that is the transuranic elements, because these elements are situated after uranium, that is atom number 92. So all these facts we know. Now, while the question of the synthesis of transuranic elements arised, first of all, in the early days, the method was followed is a neutron capture followed by beta decay method, wherein we have seen that the target nucleus, when it is bombarded with a neutron, this neutron is captured. Because the capture of neutron, the mass to charge ratio increases and the host nucleus becomes unstable, and hence it tries to become stable by the emission of beta particles. And whenever there is a beta emissions are there, a newer element is formed having atomic number increased by 1 unit. This we know. As there are some significant drawbacks in this neutron capture followed by beta decay method, the second method was followed. But this method is also significant up to certain level, because if you want to synthesize certain isotopes, then this method is fruitful. So to synthesize certain isotopes, the accelerated projectile bombardment method was used. Here, the projectiles which are used majority times, the alpha particles are used. These projectiles are bombarded on a target nucleus with a greater speed. The instruments which are used to accelerate such projectiles are heliac or cyclotrons. These are also known as accelerating projectile machines, which gives the velocity to the projectiles, and a required product have been obtained. But as the method itself is having certain drawbacks, because only certain isotopes have been synthesized, and hence this method was also outdated. Nowadays, the most fruitful method that is used is a heavy ion bombardment method. This method gives certain fruitful results because certain higher members of the transuranic series, those members can easily be synthesized by using this heavy ion bombardment method. The heavy ions which are used in this method are beryllium, boron, carbon, nitrogen, oxygen, and neon. These are the certain popularly used heavy ions which can be used as a projectiles. The method of synthesis of these transuranic elements, this method is much more superior to the earlier two methods which we have already studied. So, how a heavy ion can be synthesized by using this heavy ion bombardment method? Let us look at this method. Again, you have to take your notebook, because we have to work out certain nuclear reactions. Those are very interesting to study, and hence it is better if you take the notebook, and I will be asking you certain questions based on these nuclear reactions. So first of all, take your notebook. I shall give you one nuclear reaction based on this heavy ion bombardment method. So the method that we are following, this method, name of the method, this is a third method that is known as the third method is known as heavy ion bombardment. Heavy ion bombardment method. You write in your notebook. Now, here just now I have mentioned the popularly used heavy ions used in this process are beryllium, then boron, carbon, nitrogen, oxygen, and neon. These are the some heavy ions which are used as a projectiles which may be bombarded with the target nucleus. As we know, beryllium having atom number 4, atomic mass 9, boron atom number 5, atomic mass 10, carbon atom number 6, atomic mass 12, nitrogen atom number 7, atom mass 14, oxygen atom number 8, atom mass 16, and neon being the inert gas element having atom number 10, atom mass 22. So these are the heavy ions which are used during this course of a method. As we know, first of all, a target nucleus is there. This is a target nucleus with which a projectile is bombarded. This we have seen last time. Then a product nucleus that is obtained with some particles are ejected. These are known as ejectiles. Here, the product nucleus thus obtained is known as the recoil nucleus, or sometimes this is also known as a daughter element. This is also known as a daughter element because this element is from the parent element, that is a parent nuclide, that is a target nucleus, which gives rise to a recoil nucleus or a daughter element. Now, just take a look at the first reaction. You write side by side. First of all, we shall take the example of beryllium as a heavy ion, where we shall take the example of californium 21598, with which this beryllium 49 that is bombarded. Here, in this process, a alpha particle is ejected with 3 neutrons as a ejectiles. Now we have to find out which is the recoil nucleus or the product nucleus or the daughter element that is formed by bombardment of this beryllium. Try to solve this. Californium 98 plus beryllium 49, which gives alpha particles with the ejection of 3 neutrons. What we do? First of all, we shall add up the atomic numbers. 98 plus 4 is 102, minus 2 is 100. 250 plus 9 is 259, minus 3 is 252. Atomic number 100 is of fermium. Now, here, just by bombardment of this californium nucleus with beryllium as a heavy ion, the product thus obtained is a fermium. Again, fermium is having higher atomic mass because it is a SHE element. Now, in terms of certain notations, how can we write this particular reaction? This reaction, as we have studied last time, that here projectile is a beryllium, then ejectiles are alpha particles and 3 neutrons are ejected, and hence it is known as a Beryllium alpha 3N process. Beryllium is a projectile, alpha particles are ejectiles, and 3 neutrons are ejected. So beryllium alpha 3N process. So this is about the first heavy ion, that is beryllium. Come to the next heavy ion, that is a boron. Again, the second reaction with californium 250 98 with boron. I'm expecting the answer of this reaction from you. If you arrive at the answer, then you have to answer me by unmuting your microphone. Here, during this course of reaction, this is very simple reaction. If 3 neutrons are ejected, what is the remaining product? I have given you the hint that when such reaction is there, we have to first of all add up the atomic numbers. 98 plus 5 is 103. 250 plus 10 is 260 minus 3 is 257. Atom number 103 is of lawrencium. So lawrencium having higher atomic mass than fermium, that is obtained, and as per the notations, we can write this particular reaction boron as a heavy ion, boron 509, sorry, 510. This is a projectile. Then the ejectile is a 3N process. So boron 3, boron 510 3N process. What we call this as a boron 510 3N process. Come to the next heavy ion, that is a carbon. For carbon, we shall have uranium 23892 nucleus. This is a stable isotope of uranium, wherein if we bombard this with the help of a carbon 612, during this course of a reaction, if 4 neutrons are ejected, to arrive at the products, first of all, we have to add up 92 plus 6 is 98, and 238 plus 12, 250 minus 4 is 246. Atom number 98 is of californium, as we know. So this particular reaction in terms of notations can be write 6 carbon 612 4N process. This is how one can bombard this uranium 23892 nucleus with carbon as a heavy ion. Next heavy ion is a nitrogen 714. The fourth reaction again with uranium 23892 nucleus, which is a stable nitrogen 714. During this course, if 6 neutrons are ejected, now here, if 6 neutrons are ejected during this course of analysis, now 92 plus 7 is 99. 238 plus 14 is 252 minus 6. So it becomes 246. Atom number 99 is of Einsteinium. So this is the element that is known as Einsteinium. In terms of notations, how can we write? We have to write the projectile first, nitrogen 714, then the ejectiles 6N. So nitrogen 714 6N process. So this reaction is known as a nitrogen 714 6N process. Then the fifth heavy ion after nitrogen is oxygen. So by taking the same example of uranium 238 92 nucleus with oxygen 816, here if 4 neutrons are ejected, we have to arrive at the product of the main reaction. Now 92 plus 8 is again 100. 238 plus 16 is 254 minus 4 is 250. Atom number 100 is of fermium. In terms of notations, we can write this particular reaction as oxyl 816 as a projectile, and 4 neutrons are ejected, hence it is a oxyl 816 foreign process. Then the last reaction for this heavy ion bombardment method is with this neon 1022. So neon 1022 with the same target nucleus, that is a uranium 23892 nucleus plus neon 1022, which gives again 4 neutrons are ejected. Now, once we know the particles which are ejected or which are known as ejectiles, one can easily arrive at the product of the main reaction. So 92 plus 10 is 102, and 238 plus 22 is 260, minus 4 is 256. The element is nobelium. So this reaction can be written in terms of its notations as like this: neon as a projectile 1022, 4 neutrons are ejected. This is known as a neon 1022 foreign process. So this is how we can synthesize certain higher members of the series. See here, fermium is obtained, lawrencium, californium, einsteinium, fermium, again nobelium. So all these are referred as a heavy ions which are obtained just by bombarding these with the help of some heavy ions. So this is all about the heavy ion bombardment method. So if in certain cases the heavy ions are required for research purposes or some other purposes, then this method is very much fruitful. Now, the last aspect of this topic, that is chemistry of block elements, is IUPAC nomenclature. IUPAC nomenclature of super heavy elements having atomic number greater than 100. So we have to give a perfect scheme for the naming of all these elements having atomic number 100. So in the early days, the scientists were thought of that if at all the element having atomic number 100, then how can we name? Similar to that in the beginning of this topic, we have seen that the elements which are synthesized artificially, those may be given the names of scientists or the names of the planets or the names of the areas where these elements were discovered. Similarly, the scientists were thought of if the atomic number is greater than 100, how can we name all such elements? So IUPAC means it is known as the International Union of Pure and Applied Chemistry. So it is an internationally based committee which decides the names of newly synthesized or newly discovered elements. So this committee decides what name should be given, and the naming should be universally accepted. So in order to give the universal nomenclature for the elements having atom number 100, a scheme was decided. So the IUPAC, this committee proposed a nomenclature system for the elements having atom number greater than 100, that is what we call as a super heavy elements, and this system includes certain rules. Which are those? The first rule number 1, first of all, the roots were chosen. The roots were chosen and the names are given to these roots, and these names must ending with IUM. What is the first rule? The first of all, the roots were chosen for the 3 digits. The roots were chosen for 3 digits. This is very important, very interesting to study. So 3 digits means here we have considered atomic number 100. So first number, first digit, second digit, and the third digit. So for these 3 digits, the roots were chosen and the names are ending with IUM. For example, we know if it is Mg, normally we write the name as magnesium, or if it is Na, we write it is as a sodium. If it is a K, we write normally it is a potassium. So everywhere we have found that these names were ending with IUM. Similarly, when the roots were chosen, we have to give the names for these roots, and these names should end with IUM. How can we give the names for the numbers? For example, if we choose the digits or what we call as the numbers, you write in your notebook. This will be easy for understanding. And the roots. Now we know the digits starting from 0 to 9. So the atomic number may be falling in between 0 to 9. So if it is 103, we have to give certain names. So the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you have to write these numbers starting from 0 to 9. So the number may be falling in between these 0 to 9. Now we have to assign the names for these numbers in the form of roots. So whenever in an atomic number 0 number comes, we have to give the name, root name as a nil. Nil means 0. So you have to write below 0, you have to write nil. Whenever in an atomic number the digit 1 comes, for this digit 1 we have to write un. So this we have to write un. For the digit 2 we have to write it is a by. For digit 3 we can write this is a try. For digit 4 we have to write it is a quad. For digit 5 we have to write this as a paint. For digit 6 we have to write it is a hex. For digit 7 we can write it is a sept. For digit 8 we can write as oct. And for digit 9 we can write n, E-double-N. So this is how we can give the roots for the numbers for this. For 0 nil, for 1 it is un, for 2 it is a by, for 3 it is a try, for 4 it is quad, 5 paint, 6 hex, 7 sept, 8 oct, and for digit 9 it is n. And as per this rule, the name should be ending with IUM. So how can we write? The second rule is that, rule number 2, whenever we assign the names for these roots, here, as per this rule, here, these names should end with IUM. How can we write? Here, if we go on writing IUM, this becomes nilium. This becomes unium. So this is a nilium. This is a unium. This is, if we proceed further, by IUM, because the end name should be ending with IUM, and try IUM. Then quadium. And but the problem arises while writing certain names. For example, by IUM and try IUM, and the third n nil. Sorry, it is NIUM. So these are certain members where certain difficulties were arise because here by IUM, try IUM, the alphabetic letter I comes twice, and here IUM while writing the I or after, if we write here 0, then this becomes N nil. So these are the certain problems which were arise. In order to have a clear understanding, this by IUM is later on shortened to bium, and tra IUM is shortened to trium. So TRIUM, BIUM, and here N nil becomes NL. So these are certain changes were made while naming the rules. So you will come across how this naming is simple and how the symbols are behaved. Now, the third rule, that we have to assign the symbols similar to that of we have already studied. While giving the symbols for the periodic table, we have chosen certain first letters of all these elements. Similarly, we can choose the symbols, but while choosing the symbols, we have to give a blend of a Greek and a Latin names so that the symbols all are different. So the combination of Greek and Latin names ensures that the symbols are different from one another. For example, now if we go on starting the naming all these elements, then for example, you have to prepare 3 columns in your notebook. That first column is of atomic number, second column is a name of element. It's very simple because during exam time you will be given the name of SHE element and you have to write the name of the element, or you will be given the symbol of SHE element and you have to arrive at the name of the element, or alternatively you have to arrive at the atomic number, and here the last column is a symbol. This is very simple to understand. So I think you have prepared these 3 columns: atomic number, name of element, and symbol. If atomic number is 101, so if atomic number is 101, then here the digit 1 is there. For digit 1 we have to write un. Then I shall give here hyphen. 0 digit is there. For 0 it is nil. So un-nil. And again there is a 1 digit. So it is again un, but the name should end with IUM. So we have to end with this name as IUM. So un-nil unium. Un-nil unium. And how can this the symbol can be derived? Here we have to take the first letter of every digit. That is, first letter is U. Here for this nil is N and symbol is U and U. Un-nil unium. So it is very simple. Suppose if we arrive at atomic number 2, 102, then again we have to follow the same procedure. For digit 1, we have to write again un. For digit 0, again we have to write nil. And for the digit 2, the root name is bium. By IUM is shortened to bium. So here we can write as bium. So un-nil bium. How can we arrive at the symbol? First letter is U, here N, and here B. Un-nil bium. Very simple. Then 103. Again for digit 1 it is un, for 0 it is a nil, and for 3 it is, here I have written IUM becomes a triumph. So we have tried this is as a triumph. How can the symbol can be derived? Here the symbol is first letter is U, for nil it is N, and for triumph it is a T. So it is UNT, unnil triumph. So sometimes during exam you will be given this symbol and you have to arrive at the atomic number, or the atom number may be given and you have to arrive at the symbol, or you will be given the name, you have to arrive at either the name, atom number, or the symbol of the element. For 104 it is unnilpodium, unnilpodium, U and Q. Then 105 it is unnilpentium. It is unnilpentium, UNP. So I have given here the symbols and the name of the elements, where for the proper understanding I have given the hyphens, but while writing you should omit these hyphens and the name is in complete form. For example, like this 106, this is unnilhexium. For 6 it is hex becomes hexium, unnilhexium, UNH. Now 107 unnilseptium. For 7 it is sept, and hence unnilseptium, UNS. 108 unniloctium, UNO. Then 109 unnilenium, UNE, unnilenium. And for 1010 it is, for digit 1 it is un, for digit 1 again it is un,